Hello, IB. We're going to take a look at 12I today, looking at parallelism of vectors. And specifically, this is going to work for all of our two-dimensional and three-dimensional vectors and non-zero vectors and non-zero scalars. Because think about it, if we have a zero vector, right, we won't be able to discuss a parallel vector to it. So we have looked at this idea a little bit already, where if you have one vector, we'll call this vector A, and we have another vector that we're trying to make parallel to it. If I were to take A and multiply it by 2, what would wind up happening to this vector? So if I take the length of this vector and I multiply it by 2, I'm really just going to extend the length of the vector out twice as long. Now the question is, does that change them from being parallel to now not being parallel anymore? So if we take a look at them, they'll stay parallel if we multiply them by a scalar, a positive scalar. So what would happen if I multiply by a -2? All right, so my length would double and my arrows would take me in the complete opposite direction. And again, I would still have a parallel vector, but I would just now be heading in the exact opposite direction. So any scalar, a non-zero scalar multiplied by a vector and set equal to that original vector will wind up also finding a parallel vector for us. And you guys actually proved this idea in your last section of your questions from a few nights ago. So if you have the magnitude of one vector, it's equal to the magnitude of, and that vector equals a scalar times another vector, then you guys wind up taking the magnitude of each, the scalar and the actual vector. And you guys proved this, I believe, back about 2 sections ago in your homework. All right, so let's take a look at how we actually apply this to some of our questions. All right, so putting this into practice, if we have vector A and vector B, and we're told that they're parallel, we need to find what R and S are. So we're missing 2 of our components in the second vector. And what we just discussed is that 2 vectors can be equal by a scalar. So if I set vector A equal to vector B by a scalar, that scalar will help us to figure out what we need to multiply vector B by in order to get A. Now, somebody else in the room might have set theirs up saying, well, that means vector B would be equal to a scalar times vector A. So let's see if these both actually work out. So vector A would be 2, -1, and 3. And I'm going to multiply a scalar, we don't know what it is, by vector B, -6, R, and S. So we can find that scalar by using the one set of components that we actually do know. So 2 is equal to scalar k multiplied by -6. So therefore 2 is equal to -6 times k, and this would give us k is equal to -1/3. So once we have that k value, that will allow us to find what R and S actually are as well. So then -1 is equal -1/3 R, and 3 is equal to -1/3 S. So therefore, R will equal +3, and S will equal -9. Now, for the other person in the room who set this up in the opposite order, and they said, okay, well, vector B, -6, R, and S is equal to some scalar multiplied by 2, -1, and 3. Then we can find our k value by saying -6 is equal to 2 times k, and here we get our scalar as -3. Now our scalar will be different, however, can we still prove that they're parallel to each other? So let's figure out what R, well, not prove that they're parallel, we're told they're parallel. Can we still find our R and our S value? So therefore, we can take R is equal to -3 as our scalar multiplied by -1. So therefore, R is still going to be +3. And then our 5 is equal to 3k. Oh, excuse me, S, thank you, is equal to 3 times 3. And that is going to make 9. So 3 times 3, therefore S is equal to 9. So they do check out. Either way that we set them up, we just wind up with a different scalar. So again, one vector can be equal to another vector by a scalar, and if that is true, then we have two vectors that are parallel to one another. So a few questions to consider before we do our last example together, and some of these have already come up in class, as I'm sure you guys can attest to. Can a vector be infinitely long? So does a vector have to have a finite length? All right, and since we talk about a vector as a magnitude and a direction, what do you think our answer would be for that one? Second, that we're going to go into, you've now learned that a unit vector is 1 unit long. So how could I force a vector to be 1 unit long? There'll be a few ideas. There's a few different ways of asking a question like that. Third question, how can we create a unit vector in the same direction as another vector? So if I want two vectors to be going in the same direction, what needs to be true about those two vectors? And then also, how can vectors be parallel but maybe be in different directions? Are there any possibilities where this is true? All right, so consider these 4 questions because we'll wind up touching on them as we go through a few different examples in class next time. We're about to go into these 2 questions right now. So talking about unit vectors and if we can create vectors that are in the same direction. All right, guys, so in example 27, you're given vector A, which is 3i minus j, and we're asked to find a unit vector in the direction of A. So I don't want to change the direction of 3 in our x direction and -1 in our y direction. However, I do want to change the magnitude because it specifically says to make it a unit vector. So that means I want the magnitude to equal 1. So using proper notation, I want magnitude of vector A to equal 1. So if that's the case, I want it in the same direction. So I'm going to set up a scalar times our vector A should equal a new vector B, and this is the one that we want to find. So this new vector B is the one that we are going to find now. We set them up as parallel to each other because we want them to be going in the same direction. And we are not making them in opposite direction because it asks us to be in the exact same direction as 3i minus j. All we want to do is change our magnitude. So from a few classes ago, you proved that if I take the magnitude of a scalar multiplied by a vector, that is the same as the magnitude of that scalar multiplied by the magnitude of the vector. And we want to force the magnitude to equal 1 in this problem. So let's go ahead and set up our magnitude. So magnitude of k, we don't know what k is, so we're going to keep it magnitude of k. The magnitude of vector A is going to be the square root of our x component squared, so 3 squared plus -1 squared. And we're going to force it to equal 1. So therefore, we get the magnitude of k multiplied by the square root of 10 equals 1. And the magnitude of k is equal to 1 divided by the square root of 10. So what we just figured out was that if a scalar times vector A equals the new vector that we want, so that A and B are in the same direction but different lengths, what we want is k, which is going to be 1 divided by the square root of 10, multiplied by A, because that tells us what direction to go, which is 3i minus j. And that gives us our new vector B that we were asked to find. So we just called it B. It didn't actually give us a name for this. So in part A, a unit vector in the direction of A. So here's my unit vector. The 1 over square root of 10 forces it to be 1 unit long, and 3i minus j keeps us in the same direction. So we've satisfied both of those requests. For part B, it says a vector of length 4 units in the direction of A. Well, since we just found a unit vector, this new vector that we just created is exactly 1 unit long. So if I want it to be 4 units long and in the same direction as A, then I'm really taking this exact same vector, but now making it 4 units long instead of 1 unit long. So for part B, in order for me to make my vector 4 units long, I would multiply it by 4. So we will take 4 over the square root of 10 and keep it in the same direction as the original vector 3i minus j. So we have satisfied a vector of length 4 units, and we kept it in the same direction as vector A. So last but not least, in part C, it says find a vector of length, or vectors, so hint, there might be more than one, of length 4, which are parallel to A. So this hits part of those 4 questions that we asked you to think about. If we want to force the length to be 4 units long, think about what we just did. We forced our length to be 1 unit long, and now in part B, we have a vector that's 4 units long. However, it just needs to be parallel to A. It doesn't necessarily say in the same direction. So how does that change the way that we would answer C, part C in this question, if we just want the new vector that we create to be parallel to A, but it does not necessarily have to be in the same direction? All right, so try part C, and we'll start with that one to begin our discussion in class. Have a good night.